I'm Sam Weber. I'm going to talk to you about the API Usability and Security project. So basically, this is an unusually structured project. So this is a nice example of the collaboration between the CMU and SEI. So on the left-hand column, we have the CMU staff, sorry, the SEI staff. And on the right side, we have the CMU staff. So Professor Brad Myers, who's over there, who's expert in usability. Jonathan Aldrich, who's this expert in software design. Josh Sunshine, who is expert in about everything. And Michael Koblenz, who is a PhD student. So basically, the aim of this project is to develop and empirically test concrete and actionable API design principles that lead to more secure code. And in general, the long-term vision is to empirically test secure development practices. As Kevin Fall said yesterday, there's the whole life cycle of secure development. And we don't have very many empirical evaluations of what value each of those parts has. And most of the development practices are based upon experience, deductions by smart people. But we really don't have very much information about the validity and relative merit of different practices. And as Andrew Meatley says in this quote, design decisions in particular have very little evidence of the merit. And this project is aimed directly at the design space, saying, okay, APIs are a really important factor in design, because when you build a secure system, one of the first things you do is divide into components and then decide how the components interact. And how that interaction is the API. And especially when you're trying to outsource components. It's all of your outsourcing, it has to do with this API. If your API was badly designed, you only find out about it once it's too late and you get the result back and it's bad. So the basic principle of this project is that programmers, designers are people too. How do we design APIs so that the results that we get back from the developers will be more likely to be secure? And we also know that this is an important question because they have a huge impact on system security. So this paper is a horrible example where Facebook's APIs, so what do you say, in a website, it says log in using your Facebook credentials. That is an API that is produced by Facebook. And researchers found that although the API was functionally correct, it was really hard to understand, and therefore most websites that used it got it wrong, and therefore resulted in insecure websites all over the place. And they're long-lasting, but are generally designed by a small number of more experienced people. So if you can build it correctly now, you have a large impact in the future. So we decided to be actionable and concrete. And to be concrete, we need to focus on a particular kind of question. So we decided on state management, because APIs usually say, here is some data structure, or here is some concept, here's some state that we're going to manipulate, and then specify how it's going to be changed or not changed by each of the parties to the API. So we're asking, how are system state changes controlled? Immutability is one of these core properties that comes back again and again. So immutable data structures are one whose value is fixed once it's created. So you make a data structure and say nobody can change it. It's good as it is. So the way we worked is to use iterative participatory design. So the way we do it is you talk to actual people in the field and ask them, what are your pain points? What are you experiencing? Why are you unhappy with the way the world is right now? Then we create prototypes to address those issues, and then we evaluate with user studies whether that worked or not. Because oftentimes, people don't know exactly what they need. And sometimes when you try, you get wonderful results, and sometimes you find that that wasn't quite what was wanted. So we're going to iterate along those 3 steps. So what we did was interview a bunch of experienced programmers with an average of 15 years of experience, and ones who have experience with large programs, many of them with DoD relevant projects. And all of them, to our surprise, he said, controlling when and where state change is changed by whom is a serious problem. Everybody said. One person, when we asked, went on a large rant about all the horrible issues he's seen involving people just misusing state. This one I particularly liked because he described an issue where he had two teams in his organization, and they ended up not being able to work together because one team had a data structure, and it turned out to be mangled by a third party. And the two teams ended up arguing about who was at fault in here. And by the time it was figured out there was a third-party code that was at fault, the two teams had such distrust they could never work together thereafter. This is really bad. And programmers do try to use concepts like immutability. They really like controlling please, I'm showing you state, do not change it. But they really can't use language features that they exist in C++ and Java languages like that. And there's a whole laundry list of just issues that come up with existing language features. So they have a great need, and the existing solutions don't work. So what we did, it was build prototypes, because again, we wanted to be actionable. And one way to be actionable is to actually show that you can make things better. So we designed 3 language extensions for Java to address the common use cases. 2 of them pertain to what data is immutable, i.e. what data you can't change, and 1 pertains to when it is immutable. And at the moment, 2 of them are fully implemented and 1's in progress. So the first 2 are both class-based immutability extensions. So this is that every object created by this class will be immutable. And the syntax, we've implemented this, is pretty simple. You annotate the class with the @ sign saying immutable, and that just denotes that, okay, this object, once it's created, won't change. And here's an example of a mistake, which we give so you can see what the error message is. So you have a container, and it contains a date. And it's marked its constructor is marked as producing an immutable object. But if you notice, the date connects, once you have this object, can be just changed arbitrarily. And so when you actually compile this, you get an error message saying that, look, you said this was immutable, but you have this date, which can change. So that's not what you said. And we have this actually counts as 2 different methods, depending upon what the definition of immutable is. So one problem, when you say an object is immutable, there's the issue of, do you mean all of the object, just all the data that it contains directly, or do you mean the whole graph at which it references? So if you have a tree structure or a dictionary, and it's immutable, do you just mean, okay, the keys and the data structure itself is immutable, but not the values in it, or is it everything? And so we have 2 exact cases. One is in which it's just the first layer, and the other which is everything refers to. And you can kind of find use cases for both. So sometimes you want the maps from keys to value to be completely fixed. See, when you get the key, you get the same value. Other times it wants just what's in the data structure, like keys being fixed. But you can have new customer record, for instance, can be updated. There's the fixed mapping between customer IDs and customers. The customers can change, but not the mapping itself. The other feature we're implementing is immutability during initialization. And this is dealing with the fact that when you're trying to construct complicated data structures, you have graphs and trees and all these complicated data structures. And both Java and C++, is final and const, its functions don't allow you to do this because you have all these objects, you're tying them together, and final doesn't allow you to do that in Java, const doesn't allow you to do that in C or C++. So what you do is you have a new type system, which says, okay, this object, foo, can be in 2 states, either fluid or frozen. And what's in fluid, you can tie things together and change it until it gets to a form that you want. And then you freeze it. And once it's frozen, it's immutable and no one can change it. And there's little subtle rules about the use of fluid objects, which I can describe offline if you need to. Okay, and then we're going to be evaluating this. So right now we're just doing test cases or evaluation mechanisms. So again, we want to do user studies to actually show how effective these prototypes are. And again, we're using participatory design techniques, including Think Aloud protocol. So you give the developers tasks, and usually before you even show them what features you want to use, you get them to describe how they think about the problem, what comes naturally to them. And then you give them the tasks and the features you want them to use, and watch them, and try to encourage them to think aloud. And this helps a lot, particularly because if you're giving them new features, you sort of expect them to be a little bit slower at doing it. But if they're slower and say, oh my God, this is so useful, then it's some indication that the slowness is just due to the fact that it's new. Whereas if they're complaining about just being really confused, you know the slowness is because, look, your design isn't working correctly. So and then you have developers use the features and discuss out loud their three strategies, thoughts, problems, and also use the standard language as well. So some of the examples we're working with is an online game scenario, because online games are a nice example where one, there's a whole bunch of concurrency involved, and everybody knows that everybody tries to cheat. And therefore, there's large problems with data structures being changed underneath you in your web applications, oftentimes maliciously. So this seems to be a nice example where programmers could use the fact that data structures are immutable just to protect themselves. And another example is bus routes. I don't know how visible it is on these slides, but you have just complicated data structures here, and asking people, here's the day routes of this bus map, and construct this, which is another route where you don't want to accidentally change the existing routes. And so it's again a matter of tying together objects in a complicated data structure. So basically, jumping back up, our goal was to develop an empirically test concrete and actionable API design principles that lead to more secure code. So in order to be concrete, we started on state management. And then in our project plan, after doing interviews, we prototyped them so we address the actionable part, and are starting user evaluation studies in order to empirically test the value of this work. So the results at the moment are that we identified a design space of state change restrictions. We confirmed in interviews that management of state is a serious problem, and the current language features are just not good for people. And we showed that various kinds of immutability features are possible, which better map to the developer needs. So far, we have 2 workshop papers, conference publication. We have another publication that's being submitted. We're crossing our fingers as to whether it will actually be accepted. So as I said before, this is a thing where it's a 1-year NSF project, which is funding the CMU side, and one year SEI project, which is funding the SEI side, and a 3-year NSF project. So the professors in the CMU side will be going on for 2 more years, but SEI, this is stopping now. So our partners will continue the ongoing work, and probably the emphasis of the project will shift a little bit towards the usability side rather than the security side.